Good morning, everyone, and welcome to my presentation, Food Packaging in the Circular Economy, where I will give an overview of chemical safety aspects for commonly used plastics. First, let me quickly introduce the Food Packaging Forum Foundation, where I work. FPF is a scientific communication and research organization focused on compiling and communicating information on food contact materials and chemicals, their migration from food contact articles, and their effects on the environment and human health. We were founded in 2012 and we are located in Zurich, Switzerland. We are a non-profit funded by unconditional donations and project-based funding, and our audience is fellow scientists, industry experts, regulators, and communicators working in the area of food contact materials and health. Today I'm going to talk about the chemical safety aspects surrounding our treatment of food packaging, and particularly of the food packaging waste in the context of circular economy. In circular economy, the value of products and materials should be maintained for as long as possible, while resource use and waste production should be minimized. One often chosen path towards this goal is the increase of recycling rates, and it is acknowledged that material cycles within circular economy should be non-toxic for human health and the environment. A set of related initiatives are united under the umbrella of the so-called European Green Deal, which was announced by the European Commission in December 2019 and described as a roadmap for making the European Union's economy sustainable by turning climate and environmental challenges into opportunities across all policy areas and making the transition just and inclusive for all. The three action areas encircled in red here are particularly important to our discussion topic today. First, there is a recognized need to mobilize industry for a clean and circular economy, as described within the EU's industrial strategy, as well as the roadmap for the new Circular Economy Action Plan, released in March 2020. In the context of food packaging, many actions within these plans focus on plastics and microplastics, as well as single-use plastics and the transition towards reusable or recyclable packaging and bio-based and biodegradable packaging. The Farm to Fork strategy, published in May 2020, addresses a multitude of contemporary problems, including environmental pollution, loss of biodiversity, climate change, and this strategy plans actions on food transport and storage, food waste, packaging waste, and it includes a revision of EU legislation on food contact materials. The Zero Pollution Action Plan is expected in 2021. It should include, among others, the chemical strategy for sustainability, and according to the roadmap published in May 2020, the existing legal framework for chemicals should be simplified and strengthened, and a more rapid reflection of scientific evidence in regulation should be made possible. There is also a Zero Pollution Action Plan for water, air, and soil expected in 2021. There are several trade-offs which need to be considered when dealing with packaging waste in the circular economy context. On the one hand, food packaging needs to protect food, extend shelf life, and it should provide information and marketing advantages, and also convenience for consumers. At the same time, undesired emissions and use of resources and energy should be minimized. These two aspects are not always easy to reconcile. The preferable actions for dealing with food packaging waste range all the way from preferred reduction and prevention of unnecessary packaging towards the undesired disposal through landfilling or littering. Here I provide a few more examples of trade-offs. For example, reusable packaging requires higher use of energy for transport and cleaning during each cycle of reuse. Then using less packaging could lead to more food waste. And design for lighter packaging items could impede collection and recycling success. The Dutch National Institute for Public Health and the Environment, the RIVEM, has outlined 10 types of Rs which are at play when dealing with material waste. As you can see here, the actions of refusing, rethinking, and reducing can reduce the subsequent waste generation even before the actual use phase. And within the different options allowing to extend the use phase, reusing offers the shortest turnaround times, while recycling typically takes much longer. Moreover, Moreover, if we take a critical look at the recycling models we have at use today, we will see that we are still far away from a true recycling economy with recurring material cycles and much lower waste generation. But we are rather at a recycling economy now, where we have each recycling round, which is in essence a downcycling to a lower quality product, quickly ending up as waste itself. As Bjorn Hansen has put it, the materials we use today are not circular, they are linear with a few loops. So what are the challenges on the way to the true circular economy? In the context of food contact materials, we can invoke the concept of permanent and non-permanent materials. So, for glass and metals, due to their inorganic nature, an unlimited number of cycles without any loss of quality is possible, while for organic materials such as plastics and paper, the problem of partial degrading with each recycling round comes up, and thus only a limited number of cycles is possible until the deterioration of quality becomes too high. One aspect crucial to enabling true recycling, that is, generating a product of the same quality as the recycled product, as opposed to downcycling to lower quality products, is the need to manage the presence or even accumulation of toxic chemicals within recycling rounds. So here we see toxic chemicals as impediment to circular economy. And in fact, the need to phase out substances of concern at the design stage of circular economy products has been recognized, for example, by the URIC, the umbrella organization for European recycling industry, within their top 5 priorities for the coming years. They have also emphasized that the design for circularity should be the rule rather than the exception. Similarly, many other organizations have recognized the need to deal with toxics within circular economy. And I just give here two more examples here. The first one is the 2019 report by RIVM, which discussed coping with substances of high concern. And the second one is the recent report by the Regional Activity Center of the Stockholm and Basel Conventions, where it was recognized that toxic plastic additives could be a barrier to making progress towards circular economy. In 2018, we have published a review of the chemical safety aspects, particularly for recycling of different food packaging materials, including plastics, paper and board, multi-layer multi-materials such as beverage cartons, as well as metals and glass. Today, I will focus only on the plastic packaging in this respect. So why should there be a particular focus on plastic food packaging? Well, first of all, plastic packaging has a very high share in global plastics production, and also among plastics has a very high share among different food contact materials. And this results in a very high exposure potential for humans and the environment. Also, plastics are associated with some known hazardous chemicals, and there is generally a very high diversity of chemicals in plastics, with many unknowns still remaining. And there have been already many concerns voiced that increased recycling of plastics could compromise chemical safety. In my next slide, I will quickly discuss these aspects in more detail. Well, first, it has been estimated that 380 million metric tons of plastics were produced in 2015, and this amount is expected to double within the next 20 years. 40% of this enormous amount of plastics is used for packaging, with about 60% of this, that means about a quarter of global plastics production, are used particularly for food and beverage plastic packaging. Indeed, rigid and flexible plastics represent over a half of food packaging materials currently in use, and many of the other materials often have smaller plastic components such as plastic lining or coating. And despite occupying the large proportion of food packaging quantities, plastics currently has the lowest recycling rate. The recycling targets set by the 2018 EU Directive on Packaging Waste for 2025 and 2030 have already been met or almost met by glass, wood, and paper and cardboard materials, and also by metals, particularly aluminum, although some more increases are still needed for ferrous metals. In contrast, recycling rates for plastics, already set at one of the lowest levels of 50% and 55% for 2025 and 2030 respectively, have still the longest way to go from the current recycling rate of 37% average for Europe. Here it should also be emphasized that different European countries have big differences in their plastic recycling rates and available infrastructure. And the situation in the US, for example, is even more dire, with actually only 9% of plastics waste reported to have been recycled in 2017. A little more is subjected to combustion with energy recovery, composting is almost non-existing, and over 70% of plastics in the US are landfilled of plastic packaging. Particularly because of the outrageously low recycling rates coupled with very high production and high market share, plastics bears a high exposure potential not only for humans, for example through direct contact with food, but also, as we know, for the environment. Disposable plastics constitute about a half of all marine litter, and many packaging items, particularly food packaging items, are in fact listed among the top 10 single-use plastic items most frequently found on seashores. So we see here, for example, drink bottles and caps, lids, cups, cutlery, food containers, packs, and wraps. Apart from the visible pollution, it has to be kept in mind that there is always an invisible component to it, namely the exposure to chemicals that can leach from plastics. Final plastic articles have in fact a very complex composition. First, plastics are made of a large variety of the so-called intentionally added substances. In the final compounded plastics material, monomers are turning into the long polymeric chains, but you can also have some residual monomers left. Different additives are being added for different functional properties such as plasticizing, stabilizing, or maybe coloring. And there can also be remains of the processing aids such as solvents, which are used during the plastic production process. However, in the final compounded plastics, you also very often have other types of chemicals which you haven't been adding there before, or you didn't add them intentionally. So this can include, for example, impurities and contaminants of the starting materials. They can be oligomers, linear and cyclic, produced during the production process or as a result of degradation. And there can also be many other reaction byproducts, breakdown products, neoformed products, many of which are actually difficult to predict in advance. And in 2018, FPF has published a dossier on non-intentionally added substances where we discuss this topic further and provide more examples and discuss how these substances can be assessed. In addition to all the chemicals which are coming from plastic polymer itself, it has to be kept in mind that plastic packaging items often are made not only of single type of plastics, but can also include other components, such as printing inks, adhesives, foils, or coatings. And these components constitute an often inseparable part of a plastic packaging item, and thus the chemicals that come with them also need to be considered when designing recycling operations. Many different types of plastic polymers are currently used to make common packaging and consumer products. As you can see here, the largest proportion of global plastic waste in 2015 was taken by polyolefins, including low-density polyethylene, high-density polyethylene, and polypropylene, while PET, polyethylene terephthalate, contributes actually only 11%, and polyvinyl chloride and polystyrene even less. On the other hand, around a quarter of global plastic waste comes from other types of plastic polymers, collectively denoted by the code 7, which can include actually many different types of polymers ranging from polycarbonate to polyamide and polylactic acid and various other bioplastics. When When comparing the proportions of different polymers in the global plastic waste with the availability of developed recycling processes for different types of polymers, we can see that the highest numbers of recycling processes have currently been approved for PET in both Europe and US. And this despite the fact that this polymer does not have the largest waste proportion, as we have seen on the previous slide, only 11%. On the other hand, much lower numbers of recycling processes have up to now been developed and approved for polyolefins, which have a very large proportion, and also for polystyrene. And even less processes are now available for other types of plastics, which may include, as we have seen, other polymers, but could also deal with specific types of multi-material packaging. The highest number of recycling processes available for PET is actually determined by the relative ease of recycling, which can be done with this polymer type. In contrast, for example, decontamination of polyolefins is usually much more demanding due to certain physicochemical properties, and as a result, there are much less recycling processes available at the moment for these types of polymers. In general, recycled plastics have been shown to contain a very high diversity of contaminants. You can see a few examples on this slide. For example, there can be flavor, aroma, and odor compounds which can originate from previous food and non-food applications. There can be oligomers, monomers, and different derivatives of these substances coming both from the production of virgin materials as well as from the degradation of the polymers during use and recycling. Similarly, there can be increased levels of additives and their degradation products, again originating either from the production or degradation during use and recycling, but they also due to cross-contamination, for example, with different other types of plastic polymers. They can also be similar to this. There can be also contamination by non-food grade hazardous substances coming again from things like mixed collection of food grade and non-food grade plastics, as well as from adulteration, but also due to consumer misuse, for example. And there can also be contamination by inorganic elements such as catalysts used during the production, but also coming from the environment and or originating, for example, from the recycling infrastructure. In 2018, we have compiled a database of chemicals associated with plastic packaging, trying to gain an overview of the diversity of chemicals which could be present in plastic packaging, both food and non-food, including both food and non-food, and also trying to identify the hazardous components which might need to be substituted to ensure safer use and reuse of recycling in the context of circular economy. So this database was based on several larger databases stemming, for example, from the US EPA, but also on the books and reports on plastics. And it identified around 900 chemicals likely associated with plastic packaging and over 3,000 chemicals possibly associated with plastic packaging. Then, using different sources of hazard information available for these chemicals, we have identified 148 chemicals among the 900 of those likely associated with plastic packaging as being priority candidates to be considered for substitution due to their intrinsic hazards. And among those 148 chemicals, there were different types of the plastic-associated compounds, including, for example, both monomers and different types of additives, biocide stabilizers, but also intermediates and a few degradation products, and so on. And the subsequent further prioritization identified 5 different phthalates as the most urgent candidates to be considered for substitution. During this work, we have identified knowledge gaps and further research needs, and particularly important was the identified scarcity of information on the actual use, which had to be summoned from general books and reports. And it was really challenging to see how little information is actually available for public access. Therefore, we decided to approach this yet from a different angle, and we have recently compiled another database which we call FCCB. This is a database of intentionally added food contact chemicals. This database currently compiles 67 lists of food contact chemicals extracted from over 50 publicly available, globally sourced regulatory lists and industry inventories. It covers all different types of food contact materials, and it lists over 12,000 substances with providing also some available information on their hazards and use. This data Similarly, using the information on the intrinsic hazards, we have identified 608 substances as prioritized for substitution based on the authoritative information sources, and we have also identified over 1,400 additional substances of concern based on predictive data sources. Now, again, this is not not all of these compounds are relevant for plastics, but plastics did contain around 300 substances which might be considered as candidates to be considered for substitution. However, what is important that even with the new approach focused on government lists and industry inventories, we again observed relative scarcity of publicly available information on the use of chemicals in actual products. That means in final food contact articles. In fact, for over 10% of chemicals in the FCCDB, there was no easily accessible information on the specific type of FCM use. And another finding was that over 50% of food contact chemicals appear to be used in just one type of FCM application, while about 1,000 chemicals are used in more than 5 different FCM types. Just to give you a feeling of the type of data coming contained in the upcoming publication, here you can see the total numbers and overlap between substances assigned to 16 so-called global inventories for different FCMs. You can see, for example, that over 4,700 chemicals could be possibly used in plastic FCMs globally, with about 1,400 substances being unique to plastics. That is, they are used only in plastic FCMs and not in any other types of FCMs. Further, we prioritized, as I have already said, over 300 substances from the plastic FCMs on the list of priority candidates for substitution based on their intrinsic hazards. Other types of FCMs with higher numbers of hazardous chemicals potentially requiring substitution include, for example, printing inks, paper and board, coatings, rubber, and adhesives. Having demonstrated the high amounts of hazardous chemicals used in conventional plastics, one might wonder whether bioplastics, currently enjoying a lot of promotion, would actually be safer than conventional plastics. Unfortunately, the matters are not so straightforward here either. First, we need to acknowledge that the term bioplastics includes several different types of materials, mixing the property of being biodegradable with the property of being made from materials sourced from renewable feedstocks as opposed to fossil-based raw materials. Thus, we have conventional plastics such as, for example, PET, polyethylene or polypropylene, which are fossil-based. They are fossil-based and they are non-biodegradable. All three of these plastics, however, can be also made of monomers gained from plant-based materials. In this case, this will be denoted, for example, as biopolyethylene, but the main property would still remain the same as that of a conventionally made polyethylene plastic, and including that it remains non-biodegradable. In contrast, some fossil source plastics can be made biodegradable, and some plastics, such as PLA, for example, are both biodegradable and bio-based. With regard to chemicals used in bioplastics, there is currently a certain lack of transparency, especially with regard to some novel biodegradable plastics. There is scarce information on specific chemicals used in different types of bioplastics, but it can be assumed that some additives would be used in both types of plastics, conventional bioplastics, and also biocides or antimicrobials could pose an additional concern for biodegradable plastics. Some recent work from the group around Martin Wagner has compared the mixture toxicity of chemicals present in bioplastics with toxicity of chemicals present in conventional plastics. Here, for example, common packaging and consumer products made of different polymers were extracted to obtain a representative mixture of chemicals which they could potentially release under different conditions. And these mixtures of chemicals were then tested in different bioassays to assess their baseline toxicity, genotoxicity, and endocrine activity. For the sake of time, here I show only the results of the baseline toxicity tests performed with microtox, which is a test based on luminescent bacteria. You can see here that while, for example, none of the PET or HTP samples exhibited any significant baseline toxicity, individual samples made of LDPE, of polypropylene and polystyrene have actually elicited a significant baseline toxicity. So the red dots would represent a sample which showed the highest baseline toxicity. And as has been expected, the highest toxicity was observed in the extracts of the polyvinyl chloride and polyurethane-based products. And what has been actually unexpected is that very high toxicity was also observed leaching from PLA-based products, so from the bioplastics. However, you would perhaps consider this to be less surprising if you remember that biodegradable plastics need or might need a higher level of biocides and stabilizers to remain functional during the use phase. A subsequent investigation by the same group has shown that there are some PLA products available on the market which actually elicit no toxicity. So they did find here some products which actually showed no baseline toxicity in this test. And this demonstrates that non-toxic chemical formulations are indeed possible and they should be strived for by all products. An interesting finding was also that some products made of biopolyethylene, and bio-PET actually also showed a significant baseline toxicity, and also high toxicity was observed in the extracts from products made of several types of plant-based materials, including, for example, starch-based products and cellulose-based products, many of which were made of regenerated cellulose, so cellophane, and included, for example, things like food bags and food wraps. In the last minutes of my talk, I would like to discuss if the so-called chemical recycling could be a better alternative to mechanical recycling procedures in the circular economy context. Recently, many different promises have been voiced in the media with regard to the chemical recycling. For example, it is said that this type of recycling may provide an end product of higher quality and can also offer a safer handling of toxic chemicals. So what is actually a chemical recycling? As it turns out, this is actually not a new invention, but it has been researched already since 1950s, and commercial startups for depolymerization of used plastics with the goal of production of new plastics have been developed since at least 1970s, however with little success so far. Chemical recycling has no formal definition, but comprises a diverse set of complex engineering technologies, two main types including pyrolysis and solvent-based processes. Here, in chemical recycling, heat, pressure, and other chemicals such as solvents are typically applied to achieve either thermal depolymerization by pyrolysis or solvent-based depolymerization and purification of polymers. It is often not recognized that many of the solvent-based processes also require application of heat and pressure. And this actually means that practically all currently available chemical recycling processes have very high energy requirements. And the end products achieved by these technologies depend first on the type of technology and on the type of post-processing which are being applied. The oil or gas achieved in the process can be either used as fuel or they can be further purified again with additional resources and energy in the end with the goal to achieve monomers for production of new plastics. In practice, the majority of realized solutions so far have been plastic to fuel, the so-called P2F, while plastic to plastic, so-called P2P processes are actually a rarity, and it has not yet been successfully realized at scale. This is very often due again to very high requirements for additional resources needed to achieve sufficient purity of the end products. And this is also due to the need to deal with toxic chemicals coming with the feedstock of waste plastics or being generated during this process. Indeed, as you can see on the next slide, incoming toxic chemicals are often retained within the process and in its end products, and additional toxicants can also be created during the process. More specifically, toxic chemicals contained in the plastic waste, such as, for example, bisphenols, phthalates, brominated flame retardants, volatile organic compounds, or heavy metals, these chemicals are often not that effectively filtered out from the end product of chemical recycling. Indeed, some of these chemicals can be thermally destroyed, but others could pass unaltered. And it can also be that the process itself would reform some of these chemicals into more toxic molecules. In addition, during the process itself, new toxic chemicals can be produced, which include volatile organic compounds, hydrogen cyanide, polyaromatic hydrocarbons, PAHs, dioxins, and high temperature tars, to name just a few. Here again, it is important to understand that chemical recycling is not simply a reversible process, and thermal fragmentation of plastics often produces new molecules which are different to the original monomers. For example, it has been shown that a high content of benzene, toluene, xylene, and diverse PAHs were formed from polypropylene, while thermal decomposition of polyvinyl chloride creates aromatics such as indene, naphthalene, and alkylated naphthalenes. Overall, diverse toxic chemicals hazardous to human health and the environment can be emitted at every stage of the chemical recycling process in the form of solid waste, effluents, or air emissions. This means that chemical recycling facilities need to be regulated and managed to avoid high-risk situations both on and off-site. At the same time, cleaning these toxicants from the process and its end products can be extremely difficult, expensive, and will create additional toxic waste streams. Many recent communications by industry trade organizations, including the European CEFIC and the US ACC, have actually promoted chemical recycling as a silver bullet, which will allow to close the loop and enable total recovery of plastic waste. However, as we have seen, in fact, these technologies are characterized by high energy inputs, process losses, and greenhouse gas emissions, and very little, if any, of the original material can ever return to the economy as new plastic. In addition, there are multiple pathways to adverse impacts on health and the environment, and these are grossly underassessed at the moment. Managing these impacts will impose high costs and operational constraints on technology operators. For these reasons, chemical recycling should be treated with extreme caution by investors, decision makers, and regulators, and much greater transparency on operational performance, energy balances, and environmental impacts of chemical recycling processes must be requested as standards. Here, I would just like to conclude with a quote by Gaia, who said that in a society that urgently needs to transition from an extractive fossil fuel economy to a circular one, chemical recycling is a distraction at best. Far more mature and viable solutions are to be found in upstream zero waste strategies which focus on reducing the production and consumption of plastic. I conclude my presentation by emphasizing that food packaging not only strongly contributes to global waste issues, but it is also a relevant source of chemical exposures. In particular, recycling needs to consider the chemical safety issues better. And it has been already recognized that currently the high diversity and complexity of packaging chemistries hinders the establishment of safe and transparent circular economy loops. In particular, hazardous chemicals of concern should be phased out at the design stage of circular products if we are ever to achieve a true circular economy in the future. In addition, the other R's in the circularity equation should receive much more attention in the future as well. With this, I refer to an overview which I have already shown today, where with incentives to either reduce the input of materials and products in the beginning, for example, by getting rid of unnecessary overpackaging items, or to apply approaches other than recycling, such as reusing, repairing, or repurposing the original items. At the very last, I take the liberty to remind you that our website at foodpackagingforum.org provides a wealth of freely accessible resources on the food contact chemicals and health. And I also invite you to join us online in a few weeks for our 8th annual workshop, which will explore how policymaking can be better linked with scientific research. I thank you for your attention and I'm happy to take any questions either now or later.